The next paper is optimizing line voltage regulators with regard to power quality, who is going to be presented by Mara Holt, who received a Master Science degree in Electrical Engineering and Information Technology from the TU Dortmund University. And currently she is doing the PhD in the Institute of Energy Systems at TU Dortmund. Her research interests include distribution system control, voltage regulation, and power quality. So Mara, when you want, please go ahead.
Thank you, Jose. In the following, I will tell you something about the power quality optimization of line voltage regulator. But first, the motivation. The integration of a great number of renewable energies in the energy grid results in a new supply structure. For instance, there is a bidirectional power flow in the low voltage grid, which leads to a voltage rise and a possible voltage limit violation. To solve this issue without costly grid reinforcements, one approach is the use of smart devices such as line voltage regulators. However, the majority of these devices carry out stepped voltage adjustments, which cause a negative effect on the dynamic voltage characteristic. In addition, line voltage regulators based on power electronics are less robust due to a relatively high failure rate. For this reason, I want to present you another line voltage regulator, which can merge a continuous voltage adjustment with a robust design. The agenda of the presentation. First, we will consider the working principle of the novel line voltage regulator, which uses variable inductors for its continuous voltage regulation. Next, we will deal with the control approach, which focuses on mitigating side effects like harmonic distortion emission and an increased grid impedance. In addition, a model is developed in this section to enable the controlled system design. And finally, a laboratory analysis evaluates the novel line voltage regulator in comparison to a stepped one with regard to power quality. Now I'm starting with a working principle and an improved setup we have established in previous studies. The elementary structure of the line voltage regulator is composed of a series transformer, whose primary winding is part of an inductive voltage divider, and a variable inductor, which forms the second part of the voltage divider. The inductance of the variable inductor can be reduced, which increases the voltage at the primary winding of the series transformer and its effect on the output line voltage. Depending on the transformer winding direction, voltage boost mode or voltage reduction mode can be achieved. Here you can see the phasor diagram for the control state with a high variable inductor. The input and output voltages have the same amplitude. And here you can see the phasor diagram for the control state with a low variable inductor. The output voltage decreases about 10%. The line voltage regulator uses an inductor in its cross branch. However, due to the series transformer, the voltage is adjusted via the amplitude and not via the reactive power flow. The inductor is used instead of a resistance to avoid joule losses. The elementary design has a main disadvantage. If the variable inductor has a high inductance in the initial state, the transformer is almost a no-load operation. As a result, the magnetizing reactance of the series transformer has a high inductive impact on the grid impedance. And as you know, an increased grid impedance causes unwanted effects, such as a reduction of a short circuit current and the interference immunity to power quality. To avoid the grid impedance increase, a significant improvement is developed in our previous studies. A second variable inductor is connected in parallel to the series transformer. By a maximal reduction of its inductance, the series transformer is nearly short-circuited, and therefore it bypasses the influence of the transformer's magnetizing reactance. As you can see here, in the initial state, the input and output voltages are nearly similar, whereas the control range stays the same, as you can see here. We built this kind of setup in laboratory. Before we start with the control approach, I briefly explain the working principle of the variable inductor. It consists of an AC and a DC winding that are wound on two toroidal cores. The cores of the inductor are driven into saturation by the extra DC winding. The saturation reduces the permeability of the cores. As a result, the inductance of the AC winding decreases proportionally. The two windings and the corresponding fluxes are orthogonal to each other. Therefore, the DC and AC windings are decoupled and the saturation affects the AC signal symmetrically. The inductance can be adjusted in a continuous way. However, due to the saturation effect, the variable inductors emits voltage and current distortions. Next, we focus on the control approach. To enable a continuous voltage control, a combined control of both variable inductors is required. The control task is to ensure that the series transformer does not work in no-load operation, yet the impedance of the cross branch should be still sufficient to limit the cross current to allow for compact components and less losses. In addition, the control approach should take into account the mitigation of voltage distortions generated by the saturation effect in the variable inductors. For this purpose, characteristic maps are determined with measurements. Each map takes into account one characteristic quantity depending on the control states of the variable inductors. Based on these maps, the best control path is selected. The output voltage variation sets the start and end point of the control path. At this point, the line voltage regulator has nearly no effect on the line, and the variation of the output voltage is nearly zero. In contrast, this control state causes a maximal voltage variation. To minimize the additional grid impedance and the impact of the magnetizing reactance of the series transformer, the control path avoids these control states. To limit the cross current, these control states are prohibited. Furthermore, the control path avoids these control states to reduce the output voltage distortion. To develop a closed loop control based on the control path, the line voltage regulator is modeled in detail. The modeling is divided in three parts. First, the circuit of the line voltage regulator and its mathematical relations are determined based on Kirchhoff's laws and the superposition principle at the transformer. Next, the impedance of the variable inductors are determined. Their impedance depend on their control states. The relationships are modeled using characteristic curves measured on the line voltage regulator in laboratory. Last, the DC circuit of a variable inductor is modeled. This model defines the time behavior of the line voltage regulator, as the DC circuit consists of a large inductivity that changes with the permeability of the core. Based on the model, which considers the nonlinear behavior of the line voltage regulator, the control system is designed. To compensate the nonlinearities in time and gain response, adaptive controllers are determined and implemented as a cascade control system. If you are interested in the detailed approach of modeling and control system design, please have a look at our paper. In the last part of this presentation, the novel line voltage regulator with a developed control system is evaluated regarding to its influence on power quality. For this purpose, the usage of the novel line voltage regulator is compared to the usage of a stepped line voltage regulator. For reference, a setup without any line voltage regulator is also measured. Here you can see the configuration of the test grid in a laboratory. A power amplifier is connected via a 300-meter cable and a transformer to the external grid. Depending on the setup, a voltage regulator technique can be linked in series between the line and the power amplifier. The power amplifier models the feed-in of distributed energy resources. This slide depicts the measurements at busbar B. Here you can see the single phasor power feed-in and the resulting voltages of the different setups. In the reference setup, the voltage signal at busbar B tracks the power signal. With the usage of a line voltage regulator, the voltage rise at busbar B should be compensated. The stepped line voltage regulator can reduce the line voltage by 10 volt. It switches on at 236 volt and switches off at 225 volt with a delay of 10 seconds. With this mechanism, the mean voltage decreases. Nevertheless, the on-off control of this line voltage regulator amplifies the voltage fluctuation and emits additional flicker. The novel line voltage regulator adjusts the voltage at busbar B in a continuous way by tracking a set point of 230 volt. Due to the slow control, rapid voltage variations initially result in control deviations. You can see here. Due to the, however, gradients of 0.14 volts per second can be completely compensated. With a voltage rise above 250 volts, the control range of the new line voltage regulator is exceeded, but still the voltage is reduced with a maximum range of 20 volts. As the voltage follows a set point, there are less voltage fluctuations and the dynamic voltage characteristic is improved. This slide gives the power quality parameters for the analyzed voltage sequences. The power quality parameters at busbar A are not influenced by the line voltage regulator as the voltage interferences expand primarily to the subordinated feeder section via the grid impedance. The stepped line voltage regulator decreases the mean voltage at busbar B to 233 volts, which is 6 volt less than at the reference case without voltage regulation. However, the stepped voltage regulation emits flicker. For this scenario, the flicker even exceeds the requirements. In contrast, the novel line voltage regulator reduces the mean voltage to 231 volt with lower standard deviation. Additionally, there is no flicker emission due to the continuous voltage control, and also the output voltage distortion increases just slightly due to the optimized combined control. Conclusively, this presentation deals with the novel line voltage regulator and its power quality optimized control. The novel line voltage regulator is distinguished by the use of variable inductors and enables a robust and continuous voltage regulation. First, in the context of the underlying paper, a detailed model is provided which considers the nonlinear behavior of the novel line voltage regulator. Second, the control approach for power quality optimized regulation has been given. And third, the laboratory analysis shows that the novel line voltage regulator has less side effects than the stepped one. These contributions provide the conditions for the upcoming file test in the distribution system. Additionally, the simulation model can be used to carry on the analysis of the novel line voltage regulator in different directions, such as the control of voltage imbalances or the interoperability with other voltage regulation equipment. Thank you very much for your attention.
Thanks a lot, Mara, for your presentation. It is time for questions from the audience. Yes, we have a question from Yonggan San. He's asking, it is possible to integrate the line voltage regulation function into the medium to low voltage transformer for the purpose of cost reduction?
So that you integrate it directly in the transformer state, like it needs a series transformer in this kind of setup. So I think it's not possible to integrate it directly to a parallel transformer. Then you need to change the setup completely. The nice feature is that you have less current in the cross branch if you use a series transformer. So it would be a completely different setup if you figure a solution for that.
Any other question from the audience? Yes, I have some questions. The first one is that you have compared your voltage regulation with conventional step devices. Have you established any comparison with, let's say, power electronic based device, like a series voltage converter, which regulates in a continuous manner also the voltage?
Not in laboratory, no. We didn't have this device, so it was not possible. Just in a qualitative way, like doing research, like I checked the device, which was built in laboratory in Switzerland, and because it uses a matrix converter, it adds like harmonic distortions, they said, but I didn't try it by myself in laboratory.
Okay, I see. And another question is regarding the operation of this device in terms of losses. What can you say about, have you looked at the losses of this device? Can you give us an order of magnitude of these losses for controlling the?
Yeah, they're mainly reactive losses, which are actually quite high, like per phase it's 1 kilovar. And the joule losses are about, depends always on the control state, but they are per phase about 200 watts. So
low losses device, right?
Kilowatt, yeah.
And my last question is, it is about what happened with the behavior of this device in case of rapid voltage fluctuations. I'm thinking about, for instance, a PV plant in a cloudy day. Mm-hmm. What happened in that case? It is possible for this device to react fast enough to compensate the voltage variations due to the variations of the active power injections of the PV power plants?
Yeah, it can react directly, but if there are like really fast voltage fluctuations who are less than 1 second, you will recognize it at the output of the line voltage regulator. But if you have slower fluctuation, which are actually more usual for PV systems, like there are fluctuations about 2 seconds or 10 seconds due to the clouds. Cloud movements, and this kind of fluctuation can be completely compensated with the line voltage regulator.
Perfect. And my last questions: you have mentioned in your presentation that you have you can compensate up to 0.15 volts per second, something like that. A gradient of voltage of 15 volts per second. Is this a, let's say, a limitation of the technology, or can be improved by modifying the design?
Oh, this is actually because of the control algorithm. The idea is to make the control algorithm a little bit slower, so there will be no interoperability problems with other devices, and you also have like a smooth control, which has no flicker effects. But it's also limited by the hardware, because you have their, the DC inductance are quite high, so it reacts quite slow, kind of. But of course, you can compensate it with a control somehow. So it interacts a little bit, like. But mainly, I fixed it with my control algorithm this time.
Okay. Thanks a lot for your answers. Any other question from the audience, please? Okay, perfect. Thanks, Mara, a lot.
Thank you.
So let's move to the next presentation.